All right, welcome back. We've arrived at the drag section. So this section has no secret at all. It's very simple. I'm gonna go through it really quickly because after all, it's just gonna be. Uh, yeah, you're gonna see. It's just a few equations. Nothing too complex. Um, no crazy analytical analysis or anything, I promise. Oh, that's a strange looking rocket. Never mind. So, remember, if we are flying at a certain angle of attack, the rocket is going to have an aerodynamics force which is applied at the aerodynamic center of the rocket, and we could decompose this force into two components. We could talk about the normal force and the axial drag, which I don't know if I put it an A or the. I put an A. Yeah, axial drag. Okay. We normally talk about these two guys separately. We've discussed how to model N and AC in section 2.2, which it looked very innocent, but yeah, I don't know how many hours of videos I talked about stability, but yeah, no, certainly not 1 or 2 hours. So now I'm going to talk about the axial drag. I promise this is way easier. The axial drag, probably in the literature, you're gonna find it probably with a D, and the non-dimensional form is this CD. Well, actually, CD0. Yeah. So CD, I believe this comes from the drag at zero angle of attack. When you have zero, yeah, that's correct. If you have zero angle of attack, well, the axial drag coincidences with the axial drag. The drag with the axial, yeah, that's right. But at an angle of attack which is not zero, well, the drag is gonna be different from the axial drag. The nice thing about the axial drag is that it's independent from alpha. Oops. Okay, so that's a very important thing to note, and it seems counterintuitive. So if a rocket is flying at a certain angle of attack, well, it should have more drag, right? Well, this isn't drag. This is axial drag. This is the component of the aerodynamic force which is projected into the axis of the rocket. But remember, this isn't drag. Drag is dependent of alpha. Axial drag, well, it isn't. That's cool. Okay, so I think I'm gonna switch to this notation just to not make you go crazy with. So I'll just call the axial drag force an A, but the non-dimensional form just CD0. So we're gonna work in the same way as we did with the normal force. We're gonna treat the effects of the rocket independently. So the overall axial drag coefficient is gonna be the axial drag force due to the fins, and then the axial drag force due to the body. And I consider the body the from the nose to the cylindrical section and the boat tail. In other literature, maybe you'll find it split up. So just take that in mind. And then drag is due to 3 different, let's say, independent mechanisms, let's say. So we have friction drag. This is due to the skin friction coefficient. Okay, so it's just like the friction, let's say, the friction the part does with the air. Then we have base drag. Maybe sometimes it's called pressure drag. So if we have a ball and we have incident velocity, due to the viscosity, the boundary layer isn't attached. This would happen if we had a potential flow, but of course we have a viscous fluid, then the boundary layer doesn't attach to the body. And then here what we have is a part of a zone with lower pressure. So this lower pressure will cause some suction and some base drag or pressure drag here. So this happens the same with the body. And in the fins, because the fins are so thin, well, we don't really have this, because theoretically the boundary layer, if our wings don't stall, well, the boundary layer is going to be attached. So in our model, we're not going to have base or pressure drag on the fins. I think if I recall correctly, I think OpenRocket does add a term on base drag on fins. And then finally we have wave drag, or wave, supersonic, whatever. You get the idea. The drag related to shock waves. So yeah, shock waves, they're a non-isentropic process. We lose energy, we lose and drag forms due to the shock waves. So of course this only appears when the local Mach number is above 1. It doesn't have to be the incident Mach number. Remember, we could have some zones at Mach above 1 and get some transonic. Well, you know what I'm talking about if you're here. So yeah, obviously, well, we're going to talk about, well, each of these 2 parts are going to have, well, friction, base, and wave. Okay, so we're going to have in total, we're going to talk about 6 different axial drags, and it's just an equation. There's not much more to talk about. Okay, but yeah, we're gonna talk about maybe a few more parameters related to the fins. Up to now, we've only talked about the only relevant variables were the specific span and kind of the mean aerodynamic chord. I never remember what name we put this. I just made up this variable, but it's nice for the analytical analysis. So yeah, let's go through this really quickly.